Hello, my name is Xingling. Today I'm going to share some experience we have learned about metadata impact for deduplication. This is joint work with my grade 8 and undergrad advisors and a few former co-workers from EMC. The basic idea of deduplication is we partition the input file into chunks and identify duplicate blocks and only store unique ones. So here we have two versions of the data with only some minor modification. After we have done chunking and deduplication, the data from the second version should mostly be eliminated. And if we have many versions, we are expecting to see a good disk saving from the deduplication. So if we have two versions, we are expecting to see a 2 times the deduplication ratio. And the same applies for 3 versions. If we have hundreds of versions, then we are expecting to see a huge deduplication ratio. But in reality, we found that we only get 2 times the deduplication ratio, even for more than 300 versions of Linux. And we have come a similar situation in many other cases. So the contribution of this work is we identify the metadata impact for the deduplication. And to deal with that problem, we proposed a few solutions based on some industry experience from the EMC data domain and also the GNU type example. Now let's have a look at more closely about the metadata impact for deduplication. Metadata could impact deduplication in 2 different cases. So the first case is the metadata can be changed. This will happen when the input file is an aggregate file of many small user files. And for each user small file, there's some metadata associated. And the metadata could contain, for example, file path, modification time, and in some cases, it also contains a sequence number for ordering a file in the aggregate file. So in the input file I have shown below, I have shown previously, may actually contain 5 user files, and each one has some metadata associated with it. Well, and then even when you only made some minor modification to file 1, the metadata for other files could also be changed. Then when you do chunking, the chunks that are underlined in the second version will become different from those in the first version, and they will not be deduplicated. And this reduces opportunities and benefits from deduplication. But we found that this is actually a quite common problem. The GNU format suffers from this problem. Even some commercial backup software also suffer from similar problem, such as the EMC Networker or Oracle backups. And the video files also has a similar problem, and we will see more detail in the next talk. So second case that the metadata could impact the deduplication is the location of the metadata can be changed. This will happen, for example, the input data is encoded in fixed size blocks, and we attach some metadata for each block. Since we encode the input data in fixed size blocks, content insertion or deletion in new version will lead to the shift of some metadata. And one real world example is the table format. So, given an input file, if we encode it in fixed size blocks and attach some metadata for each block, we will have something like assume like this, and assume we have a new version and we add some new content. Again, it will be encoded in fixed size blocks, and the metadata will be inserted at the exact same offset. So if we do variable size chunking, as you can see, the location of the chunk will be shifted, and this leads to different chunks, reducing the benefits of doing deduplication. So I have go over the problem, and the solution is to separate the metadata from data. The basic idea is we want to extract the metadata blocks and store it separately from data blocks. And for different user cases with different constraints, we actually proposed 3 approaches. So whenever it's possible to change the file format, we recommend to change and switch to use deduplication-friendly formats. And we use the EMC network as a case study, which migrated to better deduplication-friendly format. When it is not possible to change the file format, then we can do application-level post-processing. This is transparent because it doesn't require any modification to user programs and also the deduplication system. Now we use the GNU as an example. When each of the previous approach doesn't work, as a last result, then we can modify the deduplication system to be aware of file formats. We use the virtual table library and local element backups as a case study. Because of time constraint, I will only go over 2 case studies, GNU and the virtual table library. So now let's have a look at this GNU tar. The name of tar was derived from tape archive, and the format was first standardized in 1988. So the format was designed without any consideration for deduplication. The tar program basically collects files into one big archive tar file, and we have seen it has been widely used for file system archiving, source code distribution, and some other similar purposes. A GNU tar file is basically contains a sequence of entry, one entry per file. Each entry contains a file header block and also a data block. And the file header block contains metadata information, such as file path, size, or modification time. So if you have a tar file containing 2 user files, we will have block layout shown below. So first have header block for the first file, and then following with data blocks. Same applies for the second file. So the problem with this block layout is the metadata embedded in the header block can change frequently, whereas the data block remains the same. So in this figure, I show the README file from 2 contiguous versions of Linux kernel source code. So as you can see, we have I show the SHA-1 value for this README file. So as you can see, we have exactly the same SHA-1 value. So that means the content of this file remains the same. However, when we examine the file attributes, the modification time is actually changed. So that means we will have two tar files with exactly the same data blocks, but the header blocks are different. Then when we do chunking, chunk 1 and chunk 2 will become different, and they will feared to be deduplicated in the second version. And this will happen a lot when you have many small files. And unfortunately, this is what we have for source code distribution. And this is exactly the reason that we only get 2 times the deduplication ratio for the Linux case. To deal with this problem, we came up with migratory tar, mtar for short. It is a new tar format and also the data transformation between a tar file and an mtar file. So giving a tar file, we want to convert into a mtar file with a migrate operation. And after the migration, we store all the data blocks together at the beginning and all the header blocks together at the end. And we store the number of header blocks at the end, as in the first block. And given that information, we can do a restore operation to get back the tar file. And this kind of migrate and restore operation is very similar to migratory compilation, which is our previous work published in FAST last year. So how effective mtar works? Where we use a non-GNU software and the Linux kernel source code distribution as the datasets. And each software has many versions, ranging from 13 versions to more than 300 versions. And the dataset, the result is shown here. X-axis shows the dataset, while X shows the deduplication ratio. The numbers in red shows the improvement in deduplication ratio. We have two findings. The first is we have seen improvement across all datasets, and the second is for some cases, the improvement is actually quite huge. For example, ranging from 1.5 times to 5 times. Basically, in general, the larger the datasets, the higher improvement we get. So we have go over the GNU example. Now let's have a look at the table library. A VTL is basically a disk-based system to emulate a table library. And when we store and input data into a VTL, the table recorder will write the input data in fixed size blocks. And for each block, it attach a block marker for each block. And in the block marker, it contains information such as which device or timestamp of file is written. Since the table recorder encodes the input file in fixed size blocks, content insertion or deletion can lead to the shift of the block markers, and this reduces the benefits of deduplication. So to deal with this problem, we can actually use another approach, which is called the format-aware deduplication. So the idea is we can modify the deduplication system to be aware of the input file format, and we can extract the metadata and store it separately from the data block. So given an input file encoded in the table format, the deduplication system can actually detect its format and extract all the block markers and store it separately from data. And during readback, the block markers can be reintroduced before returning to applications. How much benefits we get from this optimization? Well, it's actually quite huge. So we have seen 75 improvement in deduplication ratio with this optimization. And there's more results in the paper. I have go over 2 case studies, and you can read more about the other tool in our paper. And the mtar source code is also available with the link provided at GitHub. So to conclude, I have shown the impact metadata has for the deduplication, and metadata changes frequently, and that has a significant impact for the deduplication. So our solution is to separate metadata from data, and we have seen huge improvement in deduplication for some datasets. So I hope you have learned something from my talk. And if you are considering to use deduplication, do remember, do not let metadata eat away your deduplication.